Hello everyone, this is Dr. Zach. For Unit 3, Lesson 2, we are once again going to discuss the role of integration in the study of work. There are at least two different ways to think about delta W. We can discuss force being multiplied by a distance increment. Now, this is when your object that is being moved stays intact, but the force required changes as it moves through an increment of distance. Now, this idea is going to be important when we're working with springs or even when we're working with rockets as they leave the Earth's atmosphere. The second way that we look at work is we think about force increments, and that force increment is going to be multiplied by a distance. We use this concept when we're moving sections of an object separate distances. The force needed changes because the amount of the weight lift to lift changes. We'll determine increments of force when we're working with our fluid problems or our chain problem. Please read example 1 and draw the picture to describe what's happening in this problem. So what we know is we're going to find the work required to take a rocket and move it up and out into the Earth's atmosphere. So we're going to draw the Earth, and once again we're going to set the center of the Earth to be our origin. Now the rocket is sitting on the Earth. This rocket is going to be taking off and moving in an upward direction. So as it moves in an upward direction, it's going to take work to get it out and into the atmosphere. For this problem, we're going to use Newton's law of universal gravitation, where the force is going to be equal to some sort of constant divided by the distance between the two objects. So we'll call that d squared. Now the two objects in this case will be the rocket to the center of our Earth. We're told that we have 1,000 kilograms as the mass of the rocket. Now mass is not weight. We're going to take that 1,000 kilograms and multiply it by 9.8, and that will give us our meters per second squared, in which case we'll have our force, 1,000 kilograms multiplied by meters per second squared. Now that's supposed to be equal to K divided by our distance. Now the distance to the center of the Earth is going to be your 6,370 kilometers, and we're going to square that. So what do we know? We know that K is going to be equal to 1,000 times 9.8, so there's your 9800, and that will also be multiplied by 6,370 squared. We now know our K value. So let's think about what we're trying to figure out. We want to take our rocket a distance of 800 kilometers above the surface of the Earth. So the rocket is moving upward, and it's going to go upwards another 800 kilometers. So we're going to be integrating not from 0 to 800, but from the center of the Earth to the Earth's surface, which is going to be 6,370 as an adjustment for our values to find our integral. So the delta W is going to be equal to, in this case, we're going to have the force multiplied by each one. Oh, wait, we're going to use delta X. These are traveling in the Y direction, so we're going to use delta Y. So work is going to be the integral wherever our slices occur. So that's 6,370 all the way up to 800 plus 6,370. That's in kilometers. Then we will multiply by 9800. Here's our 6370. And that's going to be squared, divided by the y squared for the distance from the center of the Earth to each one of these slices, and then we will have dy. All right, now what are we measuring this in? So we already know that the force is going to be kilogram meters per second squared. Then we're multiplying by dy, but dy again is going to be meters. So we now have our answer in joules. So go ahead and figure out what that value is, and we know we have the correct units. Now read example 2 and draw an appropriate picture. So what we know is we have a 200-pound cable that is 100 feet long, hanging vertically from the top of your building. So I've drawn the cable hanging down. I've even given it a couple of links. I need to establish where my 0 is for this vertically hanging cable. I decided to put the 0 where the links will end, which means the top of the cable is going to be 100. All right, now our goal is to find the work required to lift this cable to the top of the building. Now, here is something for you to consider. The link that I'm drawing right now needs to travel all the way up that distance to get to the top of the building. However, my second link that I have drawn in the picture does not have to travel as far in distance. So the amount of work it takes to get link number 1 to the top of the building is going to be less work than it takes to get my second link to the top of the building. For this problem, let's consider the weight of one slice of this chain. We're going to cut the slice according to delta y. So one slice, let's see here, the entire cable altogether is 200 pounds. But one slice of cable would be 200 pounds divided by that 100 feet. Or we know that it's going to be 2 pounds per foot. So if we think of force as a weight, our delta F is going to be the 2 pounds per foot multiplied by the width of each little slice. And that will give us pounds per foot multiplied by foot, which leaves us with pounds. Now, knowing that delta F is 2 delta Y, our work is going to be the integral of our delta F, which is 2, let's call it dy, multiplied by the height that each one of these little links needs to move. Now, the little link will need to move 100 minus whatever position it's in, so that top minus bottom concept is going to make it 100 minus y as the distance that each little slice needs to move. And what are we going to integrate from? All the slices can be found between the values 0 and 100. Once again, I'd like to consider the units. When we have 2 dy, that was your force, which we know is going to be measured in pounds. The distance that each slice of force travels is measured in feet. So what we have are foot-pounds, and this is your British system. Go ahead, finish up this problem. Now, I'd also like to point out that we could have changed it so that the system had the 0 at the top and 100 at the bottom, and then the distance would have been y rather than 100 minus y for each slice of force to move. You will get the same answer when you set up your work equation, still integrating from 0 to 100 because that's where each one of your y values will occur. So you'll have 2y and dy because, of course, the slice of force is still 2 dy. There are different ways to set up each problem depending on how you write your system. Make certain that you take the time to do a little bit more practice.